welcome back. That is to lecture 3. So this is our third lecture in the course unit. So the previous one was just giving a brief introduction, and let's just call it listing or jotting down a good collection of power semiconductor devices. So today let's dive deep into the very first one, that is the power diode. So before we go to the power diode, let's look at a simple signal diode, one that does not conduct more than a few milliwatts to a couple of few watts. So that is a small power diode, not like the high power. So this is high power diode. Unlike the high power diode we are to deal with throughout the course unit. So let's back up a little bit. I'm quite sure in one of your previous electronics course units you have encountered a small signal diode. What is its symbol? So the symbol goes something like that. So that's the diode D, small signal diode. So the large part is the anode. Let me denote it with A. The small part is the cathode. Let me denote it with K. So that is the symbol. So that's the symbol. What are the IV characteristics? Let's look at the IV characteristics. So the IV characteristics go like this. Let's say we've plotted the current on the vertical axis and the voltage of such a device. All right, a little bit, that's the origin. So if we have voltage right there on that axis, so and let's say we happen to throw this in a circuit which biases it, we will see what biasing is. So we will keep on increasing the voltage as we monitor the current, increase the voltage, and there is a point whereby we are not going to see any current, any noticeable current. So the current flowing will be negligible. Let's say if we forward bias the diode. So that means the positive side of the source goes or is first in line with the P side. This is the P side. This is the N side of the diode, not the H, but the N side of the diode. So if we forward bias it, that means the N side, the negative side of the circuit, is to the other side, is to the cathode. So that's what we call a forward bias. All right. So let's say we forward bias, we increase the voltage. What we have control over is the voltage. Then what we are monitoring is the current in amps, voltage in volts. So we reach to a point whereby we are starting to notice a current flow. So, and at that point, that voltage is what we call VTH, the threshold forward voltage, a voltage beyond which a diode will behave as a switch in full on conduction mode. So the first bit is a bit curved, then the last bit is a bit linear. So if now, so that is scenario 1. So if now we reverse bias the diode, what happens? So if that means we flip the voltages now, this side negative, that side positive. So this is what we will see. We'll have some current flow, very negligible, negative current, very negligible, close to zero. Up to a certain point, we will see a huge current flow, huge, almost instantaneous current flow when we reach a certain point, and this is, so the voltage at this point is what we call VBR, the breakdown voltage of that diode. A voltage, if in reverse bias, if the diode is in reverse bias, that's the voltage beyond which the diode will no longer block a significant amount of the current. So it will conduct, it will go into conduction, reverse conduction mode. So that is the IV characteristic of a basic signal diode. So what are the conduction modes? So let's look at the conduction modes. There is what we call the forward, the forward conduction mode. So this corresponds to the diode conducting in forward bias mode. So this is where the supply voltage, is greater than VTH, the forward threshold voltage of the diode. So for materials like silicon, germanium, silicon is, I think, about 0.7 volts. And this is the voltage formed across the depletion region or layer of the PN junction, right? The P and the P region and the N region of the diode. We are going to look at the internal construction. The P region and the N region form a PN junction. So that junction creates a depletion region or depletion layer. That creates, since it has electrons or charge carriers, because there are holes and electrons, positive charge carriers and negative charge carriers, they create a voltage across, or a potential difference across that region, and it is in opposite orientation to the supply voltage being applied to the diode that is in forward bias. So, and that voltage happens to be around 0.7 and 0.3 blah blah blah, and smaller voltages depending on the material that's used to make the semiconductor device. So this is 0.3 volts. It's in the volts range. So supply is greater than 0. Exactly. So that's when we have forward conduction mode. So the other mode is forward blocking. Yes, forward blocking mode, where the diode is forward biased. That's nice. In both scenarios, the diode is forward biased. All right, where should I denote it? Or let me denote it around here. So here the diode is forward biased, but we could have conduction and we could have blocking. We could have the diode not conducting. So this is when the supply voltage to the diode, the supply voltage to the diode is less than the supply voltage is less than VTH, the forward threshold voltage. Remember, this is the voltage beyond which the diode will completely conduct. It will act as an ideal switch, ideally. But in real essence, we will see that no switch is ideal. There is no such as an ideal switch. So let's get to another mode. All right, we have another mode That is the reverse blocking mode. The reverse blocking mode. That is the reverse blocking mode. Here the diode is reverse. Here the diode is reverse biased. Here the diode is reverse biased. Here the diode is reverse biased. But since we have a breakdown voltage, if the supply voltage across the diode is less than VBR, the breakdown voltage, will have the diode in the blocking mode, but in the reverse bias configuration. We can also have the reverse conduction mode, where the supply voltage is greater. Let me squeeze it here. We can have the reverse conduction mode. That is where the V supply, let me call it V supply, is now greater than VBR. So now the diode conducts either way. So this is where most diodes break down. They break down, it no longer functions as a device that conducts in one direction. Now it's a device that can conduct in both directions. Most of the diodes, this is where they give up. So that is the signal diode we covered without going into too many details. So let me just throw a little bit around something, the general construction of a signal diode. It has what we call the P region and the N region. So in between here, where these two substrates, we call them substrates, where the two substrates meet, we have what we call, let me shade it off, what we call the depletion layer or region. That's a region which is depleted of mobile charge carriers. So that's how we end up with a potential difference. So I will have demonstrations, spoiler alert, I'm going to have demonstrations, practical demonstrations with the equipment. So that means we're going to have a lecture, probably the 5th or 4th lecture is going to be about tools we use in power electronics, oscilloscopes, function generators, multimeters, breadboards, and other useful materials and tools. So getting back to topic, so the depletion region is what generates the 0.7, 0.3, 0.2, blah, 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 blah volts that we must first overcome in forward bias configuration to have forward conduction forward. How did I write the word? Forward conduction. Okay, this doesn't need to be here. Forward conduction mode. All right. So sorry guys for the misspelled words. So conduction mode. So this is the voltage you have to overcome. It widens actually the moment we reverse bias. The moment we reverse bias, that depletion region widens to a point where everything has a limit. Everything has a limit to a point whereby we are going to break the diode and force it to conduct in a direction normally it does not conduct. So that is a signal diode. Let's compare it with a power diode. All right. So let's continue with the power diode. So we've seen, let me summarize a little bit. We've seen that for a signal diode, this is the construction. I have a P region. These are the terminals we use to interface with the device. Thus, the N region. So this is a substrate made of a certain material from the periodic table, semiconductor, and another one. So this region is heavily doped with holes. This one, or positive charge carriers. This region is heavily doped with negative charge carriers. Those are electrons. So that's the general construction. We've seen the IV characteristics. The IV characteristics manifest an exponential rise of the current. Exponential rise of the current, conduction current, then linear. Finally, linear relationship between voltage and current. So there is an exponential rise of the current, then linear. So, and that's the relationship between the voltage and the current. Voltage drop across the switch. That's before it fully conducts. Then, and the current, right? So exponential right around the corner, then linear. So that's the current in amps. That's the voltage in volts. All right, so this is the exponential part. That's the linear. That's the linear part. So that's what we've seen with a signal diode, a simple signal diode that can conduct around a few milliwatts to a few watts, right? So now let's switch over to something else, the power diode. For it, it's completely designed to handle high voltages, also designed to handle high currents. In mind, that's what strikes the difference between those two. This is for low voltage. This is built for low voltage and low current. So that's what a signal diode is for. And this is very common in telecommunication gadgets and low power circuits, LED, small LED circuits. You get the point. So for power diodes, in let's say industrial setup, let's say welding machine, we'll get to applications, let's say welding setups, high power audio equipment. So we are dealing with high voltages, high currents. So the design has to change a little. Take this example. A motorcycle is a vehicle, right? It carries, let's say, 2-3 people at most. A lorry, a truck, a bus, that's also a vehicle. It carries more load than a motorcycle does, a two-wheeler. So an 18-wheeler carries way more load than a bus, school bus, a typical school bus. So the design changes a little, or to a great extent. So long story short, there must be a change in design. So what is the internal construction of the power diode as compared to a signal diode? So this is how it's constructed on the inside. Remember, it's constructed with high currents and high voltages in mind. So that's how it could be. These are the terminals. Okay. All right. A little bit different, right, guys? This is different. So This is what we call the anode region. The anode region. This is what we call the drift. The drift region. That's what we call the cathode. The cathode region. So you get the point. So the signage simply means this is a region which is highly doped. Doping simply means adding impurities to a certain substance. So this is a highly doped substrate that is highly doped with negative charge carriers. This is a substrate called the drift region that is lightly doped with negative charge carriers. And this is a region that is heavily doped with positive charge carriers. Call them holes. So this construction gives the power diode the ability to handle high currents in forward bias. It having an extra layer with this different doping concentration, with a different doping, still n-type, but n-doping, but the concentration is different. It creates a large depletion, to the voltage in reverse bias. It creates a large depletion region that allows the diode to handle high voltages without breaking down, without exceeding the reverse breakdown voltage. Guys, the rest is almost the same. We're going to see a minor difference with the IV characteristics of a power diode as opposed to the signal diode. So that construction alone allows high currents in that direction and ensures that there is a small resistance in the forward conduction mode to the current. So that's how we end up with high current, high voltage conducting device. Still, it will block current flow in reverse bias. It will have same conduction modes as the signal diode, but with a few minor changes. So that is how a power diode is on the inside. Its symbol, the symbol, what's the symbol like? Guys, it's no different. It's no different from, let me just denote it with capital D. So that is the symbol of a power diode. There isn't much to it. That is it. So that is the power diode. That is its symbol. So what are its IV characteristics? IV, current voltage, X6 characteristics. So how does it behave? So when forward biased, like any other diode, before we reach the forward threshold voltage, we will have no noticeable current. I in amps, V in volts. All right. So, but notice the way the voltage current relationship behaves right after the supply voltage exceeding the forward threshold voltage of the power diode. So we only have a linear rise in the current. The current rises linearly with respect to the voltage. In reverse, we'll have something similar. That's VBR. So that's how a power diode is. So let's look at the typical applications of both, or where one stops and where the other ends. Let's wind up this lecture with the applications of power diodes. We are not going to mention all of them. There are way too many. They are way too many. There are way too many. So the very first, I'm just going to list fields of engineering. Renewable. 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 In the renewable energy sector. That's where power diodes are in the renewable energy sector. That's where power diodes are used. So in let's say in converter circuits like buck boost converters, sepik converters, and other types of converters, buck boost, sepik, buck boost, resonant converters that do the charging, that convert solar panel voltages and currents to a voltage and current the batteries can safely charge, okay, and safely discharge. All right. So charge controllers, for example, I'll be specific and say solar charge controllers, things like reverse voltage protection and reverse voltage protection circuits, or blocking diodes in solar panels. So the other is in rectifier circuits. These circuits convert AC to DC. It could easily be single phase or three phase. These are rectifiers. They could be half wave rectifier, full wave rectifiers, and more. But we use power diodes. We can use this in the automotive. In the automotive industry, things like freewheeling diodes in relays or electromechanical switches. Would use it in freewheeling. We could use it as freewheeling diodes. We could use them as freewheeling diodes in automotive industry. Motors, because in the automotive industry we have motors for wipers and what. These devices need freewheeling circuits. Where else? DC to AC converters. In DC to AC converters, these are commonly known as inverters. Right, these are normally known as inverters. So the uses of diodes are very many. Power diodes are very many. Very many. So we could use them in when we are combining DC sources. DC voltages from different sources, right? We don't want current to flow, current from one power source flowing into another power source. We could have diodes placed in series. So there are very many configurations of diodes, power diodes, that can have real world applications. So guys, allow me to stop here. So the rest is up to you as learners to go deep and research or consult if there is any challenge you face. So thank you for being great listeners and attentive learners. See you next time.